Good evening, ladies and gentlemen, and welcome to the Space Telescope Public Lecture Series. I am Dr. Frank Summers of the Office of Public Outreach, and it is my pleasure and joy to welcome you here each and every month. And when you come in, there are lithographs. Tonight's lithograph, chosen by our speaker, because she will mention it in her talk, is the extreme deep field. You want to know what that means? Turn over. We got about 300 words describing this Hubble observation that was released like 2011, 2012 time frame, and all of the thousands of galaxies that you are seeing in the extreme deep field. Our speaker tonight is Kelsey Glazer from Towson University, and she'll be speaking on Olbers paradox and gravitational light deflection. Next month, we have a special date. Okay, we usually skip the day after New Year's. It would have been January 2nd, and people tend to be otherwise engaged at that time. So we usually skip that. And then we're going to put it on January 9th, but the American Astronomical Society meeting is in Washington, D.C. this year. So lots of people from this building will be down in D.C. It's very hard to get a speaker for January 9th. So at the speaker's request, I moved it to January 16th, okay? So not the first Tuesday, not the second Tuesday, but the third Tuesday next month. This is one of the few times I've ever done that, okay? But it's worth coming to see because it will be Webb in 3 acts: the telescope, the science, the legacy. And it's such a big topic. We have 3, not 1, not 2, but 3 speakers for you. Nicole Lewis, Bonnie Meinke, and Klaus Pontoppidan will be giving you the lowdown on the next great observatory, the James Webb Space Telescope. In February, we will have Hannah Wakeford, and she'll be talking on the wildest weather in the universe. And that will be a talk on the weather on extrasolar planets, not planets in our solar system, but planets outside our solar system. For information on this and other talks, you go to our webpage, go to your favorite search engine and put in Hubble's Space Telescope Public Talks. You'll find this web page where we have a link, the descriptions of the upcoming lectures. We have a link to watching it on YouTube and our webcasting site. We have past lectures back to 2005, and you can subscribe to our email list for announcements. We've actually gotten like almost 600 people on our announcements list. It's kind of nice. We have, if you would like to sign up for the announcements, this seems duplicitous because duplicate because I just said it. But anyways, sign up at the website, the easiest. Or if you don't like doing that, you can just provide your email address to me, and I will make sure you get on it. If you have comments or questions, you can send it to this email address, publiclecture@stsci.edu. If you like social media, we are available on Facebook and Twitter and YouTube and Instagram. And myself, I do Facebook, Google, and Twitter every now and then, and sometimes write blog posts on Hubble site. I spend too much of my time working that I don't spend enough time social mediating. Oh well, there's only so much time in life, right? Observatory, the weather is not permitting. Now, how many people were here last month? And remember that the Maryland Space Grant Observatory closed for repairs. They got the repairs done, okay? So it is back in business, okay? So even though we're not able to do it tonight, it is available. If you go to md.spacegrant.org and click on the observatory, they do have open houses on Fridays. And see this observatory status box over there? That is where you will find out, if you check on Friday afternoon, early Friday evening, whether or not there will be open for observing that night. Okay, so come support the Maryland Space Grant Observatory. And now our news from the universe for December 2017. Our first story tonight, echoes of a dying star. Now, we have had a very famous press release over a bunch of years. And it involved the star V838 Monocerotis, okay, or V838 Mon for short. And this star went nova in March of 2003. This is a picture from the U.S. Naval Observatory of a star going nova. And that basically means it brightened. Okay, it had an explosion on the surface, basically, and it brightened. Okay, the star did not explode, but it just had an event for the nova. Now, this became very famous in Hubble lore because the light from that explosion spread out across space, and we watched it for several years. So in May of 2003, here you can see the star in the center here has gone back to its normal state, but the light is actually going through the dust clouds around it and illuminating those dust clouds. And over the years, as we watched it, that light expanded farther and farther into space. So V838 is one of famous ones that Hubble observed, watching what we call a light echo expand through space. The nova went off at one point, but because space is so big, it takes years for that light to propagate out through the dust cloud around it, and it illuminated different layers of that dust cloud. Now, nova happen in our galaxy, we can observe them, but supernova are even bigger explosions. And this, for example, is supernova 1987A, where a star in here brightened up to be incredibly bright. Just brightened and basically becomes the brightest thing in a galaxy for a very short time. We can see these across intergalactic distances. So the light echo from a supernova should be observable. And with Hubble, we did observe it in the galaxy M82. Now you can see this cross here in the center, okay? That indicates where the supernova went off, all right? And the supernova went off, and we started to see the light echo propagating around that supernova. So from the distance of M82, we're able to see the supernova and then go back in and reprocess images taken by Hubble of M82 later to be able to pull out the light echo from it. All right, so here is a video. Let me start it for you. Whoops. All right, so this video is going to zoom into M82. It shows you the Big Dipper, which is part of the constellation Ursa Major. And just above Ursa Major, we'll pull into the galaxy Messier 82. And this is the Hubble image of M82, and all that red is the H-alpha emission from, the starburst in the center. But we're not worried about that starburst in the center. We're worried about one particular star that went supernova way down deep inside this galaxy. Yes, see how far we have to zoom in order to see this. All right? Okay, and here's a time lapse of it, sort of an animation of the explosion. And we can process it to pull out the light echo. So although that star has died, its light lives on, echoing through the gas clouds around it for years afterwards. That's kind of cool. Our second story, rendezvous with drama. Well, we had an interesting observation occur in October. On October 19th, I know this says October 25th, but that's when this graphic was made. On October 19th, the Pan-STARRS 1 telescope observed what it thought was a comet. And it gave it the provisional designation C2017U1. Well, after just a little bit of study, they could tell, well, there wasn't any coma around it, so it can't be a comet, must be an asteroid. Then it was given this designation, A2017U1. Then after following it for a week or two, they're able to determine an orbit for it. And the orbit of this is hyperbolic, which means it's not bound to the sun. Okay? It's on such a speedy orbit that it's going to escape the solar system. It's coming through. You can see it came through closer than the orbit of Mercury, and it's headed out. It was actually discovered on its way out. So this is a hyperbolic orbit, which the simplest explanation for it is that it's not of this solar system, that is actually interstellar in origin. This has been touted as the first interstellar visitor to be observed. Now, when we predict how many things from other solar systems should be passing through our solar system, we say that there should be about tens to hundreds of these a year, right? But we've never seen one that we can say, oh, here is the observation that says, yes, this should be interstellar. This is the first one, okay? The first interstellar visitor, as people have want to call it. So, of course, everybody who had a telescope was going out and looking at it, okay? And they did so with the very large telescope, and they got this observation of it. Can you pick it out? No. So let's give you the arrow. All right. That is it right there, okay? That is an observation. And people were measuring it with various telescopes around the world and basically trying to get all the characteristics of it. And one of the most intriguing characteristics of it is that its brightness changed. So this is the magnitude, the brightness, and you can see that it's going up and down by a large amount, okay? A very large variation in the brightness. And so the one paper, which got a lot of press from the European Southern Observatory because they put out a press release about it, determined that it was small, about 400 meters, and had a very long, elongated aspect ratio. To explain this light curve, they deduced that it was an aspect ratio of 10 to 1. About 400 meters long and only about a tenth that width. When they did that, they put out an artist's illustration of it. So this is what you may have seen floating around the internet. This image of, here is the picture of our first interstellar visitor, and it has this unbelievably long, thin profile. All right? That's crazy. That's just plain weird. We don't get things with a 10 to 1 profile. We've never seen a 10 to 1 aspect ratio in our solar system. This is just sort of mind-blowing, okay? And of course, everyone said, hey, you know what this looks like? This looks like a spaceship, okay? And it matches with the reason why I call this Rendezvous with Drama is because it matches the opening of Arthur C. Clarke's book, Rendezvous with Rama, where an alien spaceship flies through our solar system, etc. And so we were all excited about it. Oh my gosh, it's got all these crazy characteristics. It must be aliens, yes! It's not aliens, okay? The internet loves this. They love to jump the gun, and they definitely jumped the gun here. So I thought I would just give you a little bit of a summary of what we do know about Oumuamua, okay? That is I believe it's a Hawaiian name for something about a visitor. I can't remember what it means, but it was hard enough just to try to remember Oumuamua. Okay? Trying to get that pronunciation was difficult. All right, first of all, the orbit is consistent with an interstellar origin. Do we know that it truly is interstellar in origin? No, we can't prove that it's interstellar in origin, but the orbit is consistent, okay? You can't argue at the hyperbolic orbit, says that, it could have definitely, a plausible origin is from interstellar space, okay? It rotates every 7.3 hours, so it's got a very, very quick. It can't be too large, okay? It's got a relatively quick rotation, and there are these large brightness variations, okay? Those are the three things in looking at the literature, that we can say for sure. Now, what's more is what we don't know about Oumuamua. Its size. The estimate that was published in the ESO press release was about 400 meters long, okay? But that was just an estimate, and there are other groups that are getting other sizes. It's not very well resolved, so it's very hard to estimate the size. You actually have to assume other parameters about the object in order to estimate that size. The axis ratio, although the highly publicized one was this 10 to 1 axis ratio, there are other papers that are down to a 3 to 1 aspect ratio, okay? So the researchers don't agree on what the axis ratio is. The color of the object, and most importantly, its albedo, its brightness, how much sunlight it reflects back, and the variations that could be on the surface, we don't know about that. A lot of that brightness change could be explained by albedo variations. For example, we have the moon in the solar system, Iapetus, which is really dark on one side and really bright on another. And that alone can produce very strong brightness variations. As if you were watching Iapetus rotate, you would get very strong brightness variations. Furthermore, the measurements of the color between two different groups are inconsistent with each other. This one here, they're uncertainties here, this one's uncertainties here, and they say they disagree at the 3 sigma level. So we don't know the color. We certainly don't know its composition yet, although if it's going to rotate in this type of speed, it should be rocky or metallic or something, should be hard. And the most important thing we don't know is the group characteristics. This is a group of 1. If this is the first interstellar object to come through the solar system that we've observed, we don't know what we should expect for these. So part of the interpretation of observations is sort of knowing what type of object you're looking at. So we're going to need more observations. Now, that's the cool thing. The Pan-STARRS project was able to trigger this, and I'll let everyone know about it and allow to observe it. We have the Large Synoptic Survey Telescope, LSST, that will be online next decade, which will be a boon for this field because it will be taking pictures of the whole sky every night. So this type of observation will be really prevalent in the next decade. I'm not going to say that I have answers for you tonight. I'm not going to say I have answers for you tomorrow, but in the coming decades, we will have lots of observations. We expect to have these kind of observations. Now, of course, we are the home of Hubble here, so half of you in the audience are going, okay, so what did Hubble see? Well, Hubble has observed this object, and that's all I'm allowed to say. We have not gotten any results that we were going to take out for press. So unfortunately, I have to leave you with the final slide that says, to be continued, okay? All right, there will be more about this object. People are studying. It's leaving the solar system at a relatively rapid rate. So people are studying it in detail. In the next couple months, all of the observations that we're ever going to get of this object will be done. And we'll see where they lead, okay? All right, so that's our news from the universe. And now we go to our featured speaker tonight. And let me get to her, whoops. You're going to have to log in. Your machine went out. All right, so our featured speaker tonight is Kelsey Glazer from Towson University. And she is, for my hosting period, the very first undergraduate we've ever had speak at the public lecture series, okay? She is on the Ernest E. Wooden Scholarship at Towson University for this year. And over the past summer, she was doing research supported by the Maryland Space Grant Observatory, the group across the street that runs the telescope. She was supported by them, working on Olbers paradox and the light deflection during the 2017 solar eclipse. And let me try this again. There we go, number 1. Now it should connect to you. There we go. Okay. And her professor, who she's working with, has already put on her webpage that she's giving a public outreach lecture at the Hubble Space Science Telescope Institute. He's got to get that right. So it's already up there about it. All right. So ladies and gentlemen, Kelsey Glazer.
As Dr. Summers said, my name's Kelsey Glazer. I'm an undergraduate at Towson University. My major is in physics with a concentration in astrophysics. And again, this summer, I was allowed the opportunity to specifically dive into these 2 subjects. And you'll hear about my research as well, but we'll also cover in this talk some of the theory behind it as well. So just to get you familiar with some of the people who were actually working with me on this, you'll see myself and Dr. James Overdoin, my mentor, in front of the Towson University 16-inch telescope. For any of you telescope enthusiasts, it's actually a Ritchie-Chrétien reflector with an equatorial mount. And in the far image, you'll see myself and Dr. Alexander Storrs atop the 16-inch, but you'll also see Mr. Chris Miskowitz and his telescope that we actually were able to take down with us to South Carolina for when we actually went to view the solar eclipse. And you also see two young ladies, Carrie McClelland and Charlotte Edwards. These two ladies were high school interns who actually came along for the ride, so it was quite a nice group, I would say. So jumping into Olbers' paradox, why is the night sky dark, right? We all agree that the universe is static and infinite, and that light is evenly distributed through it. So technically, by that definition, no matter where I look in the sky, I should always see some sort of light, a star or a galaxy, but I don't, right? The night sky is dark. It's actually more dark than it is light. That's why it's night. And, you know, why is that? If you're having a hard time understanding what this is like, imagine yourself in a forest, and you're standing in the middle of it, and no matter where you look, your eye would always hit a tree. The same thing applies. No matter where we look in the sky, technically, we should always be seeing a galaxy or a star. And it turns out, when we take our most powerful telescope, point it at one of the darkest parts of our night sky for 10 whole days, we still come up with darkness in between these galaxies. Why though? And just a quick background on this image, it's called the Hubble Deep Field. And they actually went back, the Hubble Deep Field is inside Ursa Major. And later on in, I believe, 2004, they went back and took some more images of another part of sky, and they called it the Hubble Ultra Deep Field inside of Fornax. And they took one in infrared as well, and then compiled it into the picture you're holding in your hands right now, the Extreme Deep Field, dun dun dun. And it's actually, as a quick side note, not to run off on a tangent, but inside the Extreme Deep Field, they apparently spotted a galaxy that's about 13.2 billion light years away. Now this is a significant find because that means this galaxy is lying at the very edges of our observable universe. And its age is significant, right? The universe has only existed for about 14 billion years, and this thing is almost the age of our universe. Think about, let's say you had a baby, you went to bed, and then wake up the next morning, and the baby's now an adult. That's kind of like what astronomers saw, right? The significance behind this is that, you know, galaxies take time to form, and this one is showing that it formed rather quickly. So either, you know, there's something very special about that baby, or there's something we're not understanding about the way, you know, humans develop and grow. So the existence of this galaxy that's 13.2 billion light years away makes us wonder about, you know, is this just a special galaxy? Is this an anomaly? Or, you know, is this a mistake? Or, you know, is there some crucial piece of evidence we're not understanding yet about galaxy formation? It's actually pretty neat. It's a pretty neat subject. So back to what I was discussing before, you know, the dark night sky was pondered by many philosophers, astronomers, physicists, and I'm going to talk about a few of their theories they proposed. And the title already gives it away, many incomplete answers. You'll see some, we're going to go over the ones that are really cool, but not exactly the right ones. We'll start with Kepler. He believed in an island universe, right? He believed there's the sun, there's us, and there's these glowing things in the sky around the sun, and that's it. And the thing is, right, in his universe, he has a finite amount of stars and only like a finite amount of space they can exist. However, that's not the universe we live in. We live in an infinite universe, and the light is evenly distributed through it. So Kepler is kind of outdated, and he got the boot. His theory got the boot. Going further, we have people like de Chazzo and Olbers himself, who thought, maybe what's happening is that this light is just getting blocked by stuff like intergalactic medium, like dust, right? But it's important to note that this does happen. This is happening in the universe, but it can't solely be the only answer to the paradox for two reasons. One, there can't be that much dust in the universe. There can't. And even if there was, that dust concealing all that light would start to heat up, and it then would radiate. So we would see that light as well. So it's important to remember absorption is happening, but it does not account for the entire reason why we see darkness in the night sky. Immanuel Kant is a philosopher in 1755. He came out with the idea of the fractal universe. This is a really cool theory. It's simply put there that if you take the same pattern, in this case a cross, but you can choose any pattern you'd like, and if you just repeat it over and over and over, making the scale larger and larger and larger, as it is in the image right here, you can see where certain lines of sight you would get darkness. However, Kant's proposal theory only works for small-scale universes, right? If we were to apply, this fractal, this pattern, to infinity, we would end up at the same problem we started at. We would technically then have to see light everywhere we looked, which is not the case. Therefore, a fractal universe is out. So, Zollner came next. He thought, space was positively curved, making this sphere, which would cause the universe to be unbounded and infinite, but it would make all the light inside of it finite. And going off this model here, what it would mean is that I would see a star over here coming towards me, but it would also travel all the way around the sphere, and I could see it at the opposite direction. It would be light from the same star, but just at the opposite direction. And, if we only have a finite amount of stars doing this, there's got to be lines of sight that we don't see anything. However, this theory falls through because of gravitational lensing, which is a topic we'll talk about later. But basically, not to spoil anything, what would happen is, these photons traveling through space would pass by massive objects. These massive objects, due to the warping it does to space-time, would cause it to deflect. It would defocus that light, and therefore, instead of meeting up back where it started, it would go off, right, in every direction. And then by that nature, we would then see light in every direction, and then we end up back at the problem. So curved space, goodbye. The last incomplete answer I'm going to talk about is cosmic expansion. And cosmic expansion, like absorption, is partly what's happening in the universe. But again, it can't solely stand on its own as being the only solution to the paradox. So what cosmic expansion is saying, and it was proposed by steady-state theorists, that the universe is expanding as a steady state, uniformly. Everything inside of it is expanding together, right? And therefore, by an expanding universe, it's doing two things to my photon. It's elongating its wavelength, and it's also increasing the distance it needs to travel for it to reach us, right? So it would make sense that, the more expansion, the less brightness I'm going to see, because that means more distance, and these photons have to travel to get to me. But in order for steady-state theorists' cosmic expansion to work, that would mean that the universe would have to expand uniformly. And once cosmic microwave background came around, a lot of people ended up abandoning this idea, because what the cosmic microwave background did was it showed a lot of inflation models came out as an outcome of finding the cosmic microwave background. And for those of you who aren't familiar with inflation, it is what we believe to be a point in time, right, after the Big Bang, where the universe actually expanded faster than possibly the speed of light. Now, if you're like, wait, nothing can move faster than the speed of light, you don't know what you're talking about. True, no, I'm kidding. But everything inside the universe is bound to this law that nothing can exceed the speed of light. But the universe itself isn't bound to this law. Therefore, there's technically no rule saying that the universe can't expand faster than the speed of light. So when CMB came around and gave raised to models of inflation, cosmic expansion being the sole reason why, the night sky is dark, got the boot. And of course, there's many other theories. These are just listing a few cool ones that intrigued me. This one, tired light, I really wish I could talk about. It's literally the idea that light just gets tired on its way to us. So, yeah. But there's a lot more out there, and if you're interested, there's a ton more of theories of why the night sky is dark. But to fast forward a little bit, we're going to actually look at the guy who figured it out. Recognize him? Can you believe it? A poet beat us to the answer. Dang. Now, there is some controversy over who actually came up with the solution. In Edgar Allan Poe's poem, Eureka, a prose poem, Eureka, he actually touched the subject here, as you can see, of why exactly the night sky is dark. But later, 10 years later, in 1858, Johann Madler came out with an actual paper saying this is why the night sky is dark, right? So there's some discrepancy on who they believe, was Poe hinting at it, or was he really, saying something? He's a poet. Do we want to trust a poet over a scientist? It's neither here nor there. So I'll leave it to you to decide who you think thought of it first. But I do want to read you this section of his poem because it's quite a profound statement. He says, "Were the succession of stars endless, then the background of the sky would present us an uniform luminosity like that displayed by the galaxy, since there could be absolutely no point in all that background at which would not exist a star. The only mode, therefore, in which, under such a state of affairs, we could comprehend the voids which our telescopes find in innumerable directions would be by supposing the distance of the invisible background so immense that no ray from it has yet been able to reach us at all. That this may be so, who shall venture to deny? I maintain simply that we have not even the shadow of a reason for believing that it is so." So I actually highlighted, all the theatrics, but I actually highlighted the most important part. And if you're still having trouble, kind of digging it out, because poets like to be all, ambiguous about stuff, he's basically proposing that, light has a finite speed. And it's only been allowed a certain amount of time to travel, right? And if a distance it has to travel is larger than its speed times the amount of time it's allowed to travel, what the problem is the light's just not reaching us. And that turned out to be the solution to the paradox, right? That there's the darkness in our sky is due to the fact that we just haven't received light from there yet. And if you want to think about this a little bit further and imagine the universe as this glowing sphere with a luminosity density and a radius that's equal to the speed of light, c, times t naught, the amount of time it's been allowed to travel. Here we say it is, t naught is the age of the universe, about 14 billion years old. We can relate the luminosity and the distance it's gone to intensity, the intensity of this very far distant light called, as we call, extragalactic background light, light from very far and distant sources. And to touch upon the EBL real quickly, when we first discovered it, we discovered it from a quasar that I believe was about 7.6 billion light years away. So this thing's about more than half the age of the universe. And when we detected it, in space of course, we detected it as what we call a gamma ray photon. Gamma ray photons are very highly energetic photons. They have very short wavelengths. And this raised a lot of eyebrows, right? This thing traveled like more than half the age of the universe to reach us. And even with cosmic expansion affecting the photon and elongating its wavelength, we're still reading it in as a gamma ray. It would make sense, if I drove my car from here to California, I'd have a better chance of getting into a car accident than if I were to just drive it from here down the street and back. Of course, that depends on how good of a driver I am, but that's another topic. But the same thing applies. Something traveling this great amount of distance really made us see just how empty space is, right? It's not hitting anything. It's not getting caught in any dust or any other particle floating out in space. So it actually hints at just how empty space really is. And it's quite a wonderful thing to contemplate for a second. So moving on to how this worked in with my summer research was we wanted to go out and see if we could measure this intensity from the extragalactic background light. Because by doing that, we can then make inferences about the age of the universe. Because this has traveled such a large distance, it's holding information about how long it's traveled. That T0, I would like to know. And so what you see here is that nice pink bluey picture. That is an image we took from the Towson University 16-inch telescope. And underneath it is another ground-based image of where the Hubble Deep Field is inside the Big Dipper. And we're actually aiming for the Hubble Deep Field, and as you can see, we just missed it by a little bit. They always say when you're planning telescope time, you pick 3 days. You lose 1 to weather, 1 to technical difficulties, and by the 3rd, hopefully you get something. So this falls under technical difficulties, but luckily we planned ahead and we had multiple days, but it was still a good practice to use this to do data calibration, image reduction, all these things you don't think about until you're in doing the project. But it was also taken near new moon, so we wanted to reduce the amount of light in our image because what we were looking at was something very far in distance, so we didn't want light from close objects getting in the way. And if you're curious, it was taken in the R-band filter. What that is exactly as it sounds. It's a filter that you strap onto your telescope and you tell it, hey, I know you can read in multiple wavelengths, but I only want you to look in this set of wavelengths, this range. That way you don't get light from other wavelengths that you don't care about, basically, right? So going into what we actually saw, so we estimated, assuming that the age of the universe was about 14 billion years old, we estimated that the intensity of this extragalactic background light should be about 3 nanowatts per meter squared per steradian, and that its luminosity should be about 3 times 10 to the negative 33 watts per meter cubed. And what we actually saw was what you get from telescopes is you get counts per pixel, which then you have to go and convert into the units you want. And so we converted it into 10,000 plus or minus 5,000 nanowatts per meter squared per steradian. Now, if you're like, hey, you thought you would see 3, but she's getting 10,000. Who is this chick? What is she doing? And you're right, 10,000 is a big number compared to 3, right? So what the heck happened? And I'll tell you what happened. Being a ground-based telescope, you're fighting a lot of light pollution inside Earth's atmosphere before you even get outside of it, right? So what we had to do, we had to sit down and quantify, the amounts of light pollution adding to our image from each different source of light. And after we subtracted out all those extra sources of light, we actually ended up with a really nice number of 100 nanowatts per meter squared per steradian. And this is much closer to our estimated amount, so it was quite a success. And if you're wondering what that little map of Maryland is over there, that is an image called the Bortle scale. Now, the Bortle scale tries to quantify the amount of light pollution where you are geographically. And it scales from 1 to 9, about 1 to 9, and 1 is represented as black, about 9 is represented as white, white being the worst, black being the best. And if any of you have no idea what Towson or Baltimore is, that's okay, just look at the white spot. Yeah. It would make sense, though, that in one of the most highly light polluted areas in Maryland, our data would be off because there's so much light pollution, right? So in the end of this project, we collected about 70,000 photons over a 30-minute exposure, the amount of time we left our telescope open. And we can say approximately about 20 of them actually belong to the EBL. So it was quite a fun project. learned a lot about why we want to launch things up into space, right? Ground-based is ground-based, but it was really a great learning experience and opportunity. The other half of my summer was spent actually looking for light deflection during the 2017 solar eclipse. And in these images, you'll see Chris Miskowitz with his telescope down in, all these were taken in South Carolina. But you'll see him setting up the telescope. The middle one is actually one we took with his telescope, and you'll see, the eclipse in the middle and it transiting on either end. And on the far one, you'll see me under a nice cool tent with some ice water and a laptop in front of me. I chose the right job for the end of August at 2 p.m. That is his personal telescope. I know, right? I'm very surprised he let me as close to it as he did. It's just a telescope. Yep. Who would have thought? But yeah, So I spent it was a very stressful time. We only had 2 minutes to take these images that we needed, and everything had to be perfect, everything had to be right. Clouds were coming in, threatening, and I got really anxious. I was like, you better move. And so from inside the tent, what I was doing was we were setting up, we were calibrating the telescope. I was basically saying, move it a little left, no, the other left, So in case you didn't get to see the eclipse along the line of totality, I do have a video for you taken by CNN that shows the solar eclipse as it's going through North America, right? So it starts up in Washington and ends out in South Carolina. So it's a really cool video. So here you guys go. I don't know how to do that. It had sound, but use your imagination, right? Oh, I feel bad for them.
Wow. There's clouds bad.
So it was a little video. It's actually funny because I went down to Lexington, South Carolina, and I was going down, of course, to do some imaging and research. And afterwards, I was going to meet up with some friends down at Myrtle Beach who drove 2 hours inward, to view the solar eclipse. And everything went wrong. They couldn't get into the parks because, it was backed up since like 2 a.m. the night before. And they actually met a guy there who brought him to this special spot where he was building cabins or something. It was kind of sketchy. But regardless to say, they had clear skies, and some of my friends had some small telescopes where they could view it. And as soon as transit started, clouds came in and rained on them. So one of our friends in the group chat decided to change the image of the group chat from a solar eclipse to cloudy to a cloudy sky. It did not go over well, let's just say. But eclipses, as beautiful as they are, what I was down there for was what was happening behind the scenes, right? So what is happening behind the scenes? Well, something called gravitational light deflection, right? In general relativity, we believe that gravity is equal to the warping of space-time. So what's keeping me on this floor is not some forced gravity. It's the fact that the Earth is massive, and it's dipping into the fabric of space-time, causing this little warp, and this inward warp is what's holding me down. So gravity is equal to how much warping is done to space-time. And what happens to light when this happens is light actually wants to travel on a straight path. But when it gets close enough to these massive objects and the warping that it's done to the fabric of space-time, it's going to cause the light to bend. And my eyes, you can trick them very easily. My eyes, our eyes only see in straight lines. So if I have light coming in from over here, and it's curving, and it's coming to me like this, I don't see that, oh, duh, it's light being bent around the sun. No, I think the star that the light's coming from, the star is located over here, right? If the light's coming in here, I think the star is actually over here, because I can only see in straight lines, right? And so what actually ends up happening is a star's position that we know is over here now looks like it's over here, right? This deflection is causing an outward shift in a star's position. So if I were to take the sun out of this image and have flat space, I would recognize that the star I was looking at was over here. But the fact that the sun's in there and is warping space-time and the light is being bent by it, my eyes don't see the difference. It thinks the star is over here, for sure. But it's not. And this is what we wanted to go out to see if we could see this in the 2017 solar eclipse. Right, so first we needed an equation. This is a fancy schmancy equation that basically produces a deflection of my light. Right, and this is done through a program called Stellarium. It is a planetary program, and it's made by astronomers when there's a button to take out the atmosphere. So you can see everything very nicely. And what we needed was two stars close enough to the sun that they would undergo this deflection of light. And it just so happens there were two stars that would be perfect candidates to undergo this light deflection. So it's also noteworthy to mention that these two stars are both what we call seventh magnitude stars, which means they're very, very dim. So in astronomy, we have this ridiculous scale that says the brighter the star is, the lower the number magnitude it is. So if I have like a 2 magnitude star, that means it's very bright, compared to a 7th or a 10th magnitude star, which is very faint. I didn't make the rules, I just follow them. Maybe one of you guys can come up with a better way of scaling our stars, but it's what we normally use, so that's what it means by 7th magnitude. Since they both lie on the opposite side of the sun, we estimated a total angular separation of about 0.24 arc seconds, which is potentially measurable with our equipment. So this is not what this is what we saw. What you see here is actually our telescope decided, I'm not going to work for the most important part of your project. I'm just going to conk out and not do what I'm told. So, yeah, our images look cool. But they didn't have what we needed in them, which was the stars to measure to see if this deflection actually occurred. But this is an image, and I got permission to use this image in my project from Mislav Drunkmuller. He comes from the Czech Republic, and he photographs eclipses. And if you just Google 2017 solar eclipse, Mislav Drunkmuller, he has tons of eclipses, and not just from 2017. And if you have a chance, it's really worth just pulling up on your computer, because I don't know if you probably can't see, but there's a ton of stars in this. And you can probably see, you can even see some of the cratering in the moon from the light being reflected off Earth back to it. So it's quite a beautiful image. And it works perfectly for us because it has everything we need in it, right? First, step one, we got to identify our target stars that we found in Stellarium, which, with his image, there's star A, GM Leo, and star B, HD 86898. What a phone number. Stars tend to have, we have a lot of catalogs, which give a lot of names to the same thing. So if you're wondering, hey, it says it's this star, it's just probably because that star is being named through another catalog. But it's the same star. The next step is that in order to transform the image into RA-DEC, which is right ascension and declination, it's basically how we locate things in the sky, we need to use some reference stars far enough away from this eclipse that their positions aren't going to be altered, and they're going to be fine, and everything's going to be great. So the more spread out they are, the better my solution turned out to be. So we picked some very far stars. There's that star, C, D, and E. Again, with their lovely phone numbers, identifying them. So step 3, all we gotta do now is find the angular separation between A and B and compare it to what I predicted, right? Easy peasy lemon squeezy. I was so wrong. So what made, this was probably, I wouldn't say the most stressful, because the most stressful is always setting up the telescope, making sure it works. But this was definitely one of the more gruesome parts of the research, was that this image had to be transformed from XY coordinates, pixel by pixel, into RA, right ascension and declination, locations, and a lot of things had to happen to it. So what you see here are some transformation equations that we made to account for the fact that 1, my origin needs to change. 2, beta is my scaling factor, the factor that I'm going to multiply in to turn my number that I get out into degrees, arc minutes, arc seconds, that sort of thing. And the phi is represented by the angle I had to rotate it by. So the reason I'm doing this in the first place is because if I kept the picture horizontal, my galactic north would not match up with cataloged galactic north, which would mean, yeah, I could produce some numbers, but I couldn't compare it to anything. I would have to make up my own things. I'd have to do all this stuff. So I have to manipulate my photo so that it lines up with the general standard of galactic north being up, and that now my reference stars, I can identify them through the catalog and use those locations so everything's good, fine, and dandy, right? So through this gives me 4 unknowns that I don't know about, right? This alpha delta, this new origin of my image, the beta, the scaling factor I'm going to need to multiply in, and phi, the angle I'm going to have to rotate my picture by. But not all hope is lost, because I have reference stars, yay! And I can get all of these unknowns by applying them to the reference stars, the stars that have not been changed by gravitational lensing. So once I find them for the reference stars, I can go back to my target stars, the 2 stars I believe are going through gravitational lensing, and transform their coordinates. So this involves some spherical trig. Yeah, spherical trig, good stuff. All you need to know is that, the basic trigonometry you're taught in high school or middle school, I don't know, they teach them like when they're practically elementary schools these days, I don't know. But all you need to know is that, when we do regular trigonometry with right angles and hypotenuse, right, we're normally doing that on a flat surface on like a 2D image of a triangle as such. Well, spherical trig came about because, we don't live in a flat universe. We can't use flat equations on something that's 3-dimensional. So this takes into the idea that we're applying trigonometry, but to stuff that is curved, that's not flat, that's in 3 dimensions, right? So our result in the deflected light came up to be 2,957 plus or minus 29 arc seconds in deflected. And then the actual separation, the undeflected light, being about 2,953 arc seconds. And what I want to do is I want to take the difference of this to match it to the difference of the separation I produced in my prediction to see if they're close or compatible. After doing the math, I get 4 arc seconds, which is consistent with general relativity and is very close to my predicted difference in deflection, which was 2.4 arc seconds. So this was very much a success. You might be saying, hey, her error bar is pretty high there, just like the last one. But what actually ended up happening was my mentor and I were not fluent in like coding languages such as Python or manipulation through DS9. And this image was not given to us as like a FITS. In astronomy, there's these files. It's just like another type of image file you get something sent to you by like JPEG or PDF. Well, in astronomy, we have this thing called FITS. And normally why we do it through FITS is because there's a lot of information about like what telescope took this image, where it was taken, all sorts of things like that. But that make the data calculator's life so much easier, but this image was like a JPEG. So everything had to be done manually, including the calculation. So my mentor and I actually sat down and did this calculation. So, yes, we were rushing because we were very eager to see if we saw some deflection in light, which we did. If we go back and do it a little more careful, I'm sure we can get that error bar down. But it's important to note that we are detecting an angle deflection in light, I should say, and that's consistent with general relativity. So it's quite a spectacular thing. And I was just told this earlier today, that the next 30 years worth of eclipses, there are no stars close enough to the eclipse where you'll be able to do this sort of thing to it. So we struck while the iron was hot, and voila. So, thank you. Just some last-minute acknowledgments. I'd like to thank my mentor, Dr. James Overdoin, for getting me involved, and this was an experience of a lifetime. Dr. Alexander Stores, he helped to Chris Miskowitz telescope guy. He was so nice. He let us borrow his equipment. And again, the Maryland Space Grant Consortium, the people right across the street, for funding this whole thing, because this whole thing was, I was funded and I could do it, which was great, because I don't like not being paid for things, because it's hard to live these days and not get paid for things. And they really made this whole shebang possible. And just one quick last-minute thing before I take some questions. This image is also, I have permission to use it. This image was taken by a French astronomer. His name is Jean Mouet, and I have a bunch of these, and these luckily are in FITS file, so it won't be such a nightmare going through. And I am tasked with a senior year capstone, going in and doing the same sort of treatment and seeing if I can find some light deflection in there. So this is one of his beautiful images of the eclipse, and that's what I'll be spending part of my senior year doing. So thank you very much, and I'll take questions now if any of you have them. Yeah, of course.
I always have to ask everybody this. How did you start in astronomy?
Okay, so I'm going to repeat the questions for the webcast. Okay, how did you start in astronomy?
Sure.
It's funny you ask. I was supposed to be a music education major. Yeah, it's quite a funny story. I spent my first year in college, doing what any unsure college student does, take a bunch of classes. I was very much into music, and I was preparing to be a music ed major, so I was learning other instruments, practicing on my own, and I just, Towson forces you to take these other classes that aren't related to anything else, so you become well-rounded and a well-rounded individual. So I wandered up into a general astronomy class, and I wasn't allowed to sign up until the end of registration because I was a freshman. So the only seminar left open was physics and metaphysics, taught by my mentor. And gosh, boy, did I think this was going to be awful. And it turns out that taking those two classes concurrently really made me like, oh my gosh, this stuff is so cool, And I was a little nervous because, like I said, I was so ready to be a music major, but I had a lot of help and confidence boosters from people all around me. My family, my mom, she pushed me. She was like, Kelsey, just pick something. I need you to pick something. So I owe her so much.
Yeah. That led you to the astronomy.
Yeah, that led me to astronomy. And I'm quite happy I'm keeping with it, because if it weren't for all the astronomy cool things happening in space, I don't know if I'd continue with it, because that's just because of my own personal interests. But
it's fascinating.
It is, in my opinion, it is.
Science in general. Question for you: what do you play? Because I'm music. If there's any.
Well, I've played piano since I was 4.
Oh gosh, exactly.
And I started flute when I was in middle school. But by high school, around my junior year, I just started hopping from instrument to instrument to whatever instrumentation the band needed for the band. So I ended up on tenor sax, I ended up on alto sax. My sister played the clarinet, so I tried to honk a few notes. My best friend was an oboe player, so double-reeded instruments are the devil.
I love it, that's awesome.
Are you into music of the spheres?
I'm not going to repeat that question. All right. Other questions? All right, we got a couple questions from Peter, do you have a real question?
A real question. Your description of gravity being a distortion of space-time and not a force as such. I'm thinking of the quest for the grand unified theory still hanging out there, but does this kind of destroy that effort, thinking of gravity being something apart from, the strong force and the weak force and the electromotive force?
Okay, so I got to repeat the question just to make sure people in line hear it. So your describe gravity, of course, in general relativity as a distortion of space-time. But yet there is this quest for a grand unified theory, and how does this jive with all the other forces? We actually had a question about quantum gravity online as well.
Oh, did you?
So when you were discussing this, people started thinking, the question online was, has gravity been it's 9 o'clock. Has gravity been gravity been worked with quantum mechanics?
I don't believe there's been a bridge yet built between the two. I'm not quite familiar, but as to whether there's a link between quantum mechanics and gravity yet.
Quantum gravity has not been solved yet.
Yeah, so I'm
you would have heard about it, and there would be Nobel Prizes.
Yeah, so maybe I'm not sure is my answer.
Okay, so let me explain what's happening here. When they redid the auditorium, there was an automatic shutdown that's supposed to be scheduled for 10:30 every night. Some reason this second time it's gone off at 9 o'clock while we're doing the public lecture series. So I'm going to ignore it. I'm going to pretend it didn't happen, okay?
What happened?
What? Yeah, good. Go ahead. So.
Yeah, I don't believe there is something yet discovered linking the two, so I'm not too familiar, so I can't speak on its behalf.
Okay, all the way in the back there.
What's faster, gravity or light?
Which is faster, gravity or light?
Well, that's quite a great question, actually, because,
Is there an answer? Just out of curiosity.
well, light moves at a pretty fast pace. Like, I would say light is faster, even though we have evidence of where gravity is overcoming light, such as black holes, where we can't see inside them because it's so dense that light is falling in faster than the speed of light, therefore we can't see it. But I would still say overall light is faster.
I would have to correct you on that.
Thank you. Please do. Save me.
With the gravitational, all right, so we talked about last week about the, last month and the month before that, gravitational wave astronomy, that we've detected gravitational waves. The time delay between detection in Hanford, Washington and in Louisiana correspond to a time delay of the speed of light. So this is one of the very first measures that gravity waves travel at the same speed as light does, okay? We only have a few measures, right? So, but right now it appears that the bias that we have that gravity waves travel gravity travels at the speed of light is being confirmed. Okay.
Thank you.
Good. It's all right. You're an undergraduate. You're not supposed to know everything. It's when you get a job that you have to pretend you know everything.
They constantly want us to prove that we learned something in class with exams.
All right. Okay. Did I have a question there?
Yeah, I have a question. So Einstein predicted this, right? In the early 19th century, and then or 1900s, excuse me, and some English people, I think, proved it through there was an eclipse in the 1920s.
Yeah. So
is that right?
Right. So he's referring to the 1919 total solar eclipse.
Okay. So what technology were they using in 1919 that was kind of the same as what you did in your project? Like,
Right, so
how were they able to do that?
How did they measure this light deflection in 1919 when they didn't have computers?
they use something called photographic plates, which
Photographs, what are those?
I just stand here and tell them what they want.
Okay.
No, but they would use photographic plates to take images of the eclipse back in 1919, and actually, I believe they would have to sit down and do the math that we had to do as well, right, with the spherical trig and the transformations and all that. But the difference between us, we used something on, the image we used was on something called a CCD chip, a charged coupled device. And it's a better version of a photographic plate, more portable, works better. But that's what they would use, and that's what I believe they used.
All right, so here's a question from online. You showed them the observable universe, right? That you're looking out and you see an edge to the universe. So why is every point in the middle of the observable universe?
Pardon?
Why were we at the exact center of that universe?
That was just a simplistic model. There's nothing supposedly saying that we are located at the center of the universe. I just used that shape for simplicity's sake when I went ahead and did my project. But there's no evidence saying that we are at the center of the universe. We're not going back to the dark ages of a heliocentric and a geocentric universe. So.
All right, in the back there.
A few months ago, we had a lecture where the individual said there was a lot of dark matter and dark energy, and that it covered almost the entire universe. During your lecture, you mentioned emptiness, nothing. Do both of those theories contradict one another?
All right, so does the idea of that dark matter and dark energy comprise most of the universe conflict with the idea that that you presented during Olbers' paradox, that a lot of the universe is empty?
To what I know, it doesn't really mess with the paradox or the solution. The solution to the paradox is just that the light has yet to reach us, and that's why it's dark. Not that there's dark energy or dark matter, that's what we're seeing in the sky, right? Because we can't see dark energy or dark matter, right? That's why it's called dark. It's given that mysterious name.
Does that prevent it? Does that prevent the light from shining?
It doesn't, I don't believe it does, yeah. It doesn't really interact with it. The light comes through one way or another, and it doesn't really get affected by those things.
Right. Matter of fact, if the dark matter or the dark energy changed the light in a significant way, it's a way of detecting it. And that's how, of course, we do detect dark matter, by its gravitational influence on things and such. All right, down front here.
You relate the universe with the Milky Way. How does the size? The universe, where's the Milky Way?
Okay.
Is the Milky Way
Can you relate the Milky Way's size / position within the universe?
Well, the Milky Way is 12 kiloparsecs across. The universe is large.
I love it.
compared to where we are? Where is the center of the Milky Way?
The center of the Milky Way is about 8.5 kiloparsecs from where we are, and we're in one of the spiral arms in the Milky Way. That's where we're located. I believe it's the not Poseidon, it's the Orion arm. We're in Orion spur. Excuse me. We're inside that arm. I guess my best way of saying is we're just about, if you imagine the galaxy is just like a ball or a circle, right? And here's the center. We're like about 8.5 kiloparsecs away out of that center, inside one of the arms. That's where we are. Yeah.
All right, any other questions here?
Well, I was saying,
Come on, go ahead.
Sorry, just because you said something about earlier about you didn't know about, which was faster light or gravity, and you said something. I think the best answer in the world is I don't know. I love that answer. You don't even know.
I'm still an undergrad. I'm still
I
learning.
know, believe me, everybody. Nobody knows.
Okay, we have a bunch of questions online, but they all deal with cosmological topics that they go off topic a little bit too much. I'll type in some answers for them. Next month, January 16th, third Tuesday, okay? The James Webb Space Telescope in 3 acts, okay? So third Tuesday. You all have a great holiday. We'll see you next month, and let's give Kelsey one more big round of applause. Well, you can make it.
That's an infinite.
Hold on, I was just